Alrighty guys, let's go ahead and get started with our magnetism notes, part 1. So first thing we need to talk about is magnetism and what it is. Well, we can say that magnetism is the force of attraction or repulsion that acts at a distance. This is caused by the spinning of electrons in the same direction. We'll talk more about that later on, what those electrons are, where they come from, and why they're spinning. The symbol for magnetism is going to be a capital letter B, and it just stands for the magnetic field. Sometimes we write it as B field. Let's take a look at Earth's magnetic field. Well, the Earth has a magnetic field due to its core, which is made out of molten iron. So the molten iron inside the Earth's core is constantly churning and moving around, and that's what's producing a magnetic field. Let's talk a little bit more about the Earth's magnetic field, and we can say that the magnetic field lines are going to run out of the North Pole and into the South Pole. So over here, if we take a look at this diagram, we're going to see that the magnetic field, or the magnetic North Pole of the Earth, is pointed downward, and these magnetic field lines are pushing out of the magnetic North Pole, circling around the Earth, and coming back into the magnetic South Pole. This is not always the case. A couple thousand years ago, these magnetic poles were flipped, and the North Pole was up here and the South Pole was down here. They will flip again, definitely not over our course of life, but they will flip again and again and again. It just happens every so many years that the North and South Poles flip. Something you notice though about these magnetic field lines is that they're always spaced out. They're not overlapping each other. And again, another thing that we can see is that the magnetic field lines are flowing out of the north end and into the south end. So we just saw a picture of the Earth and the magnetic field lines of that Earth with the North and South Pole. But I want to take a look at the geographic field lines. And to do that, let's just take a look at our diagram one more time. Geographic, meaning what are we used to with the Earth? What do we refer to as the North Pole? Well, the North Pole of the Earth we refer to up here, and the South Pole of the Earth we refer down here. So what does that mean? That means that the geographic North Pole is actually the magnetic South Pole, and the geographic South Pole is actually the magnetic North Pole. If we take a look at our diagram once again, we can see that here. The North magnetic pole is pointed over here, which is on the South geographic pole. And then vice versa, the North geographic pole is pointed on the South magnetic pole. Some of you might be asking yourselves, why is this important? Well, obviously this is important because this is the main reason nobody has ever been able to find Santa, right? We learned that Santa was at the North Pole. But what if this whole time, instead of the geographic North Pole, it actually was the magnetic North Pole? That would mean that these people were searching for Santa in the wrong location all of these years. Let's take a look at iron, because iron is a very interesting type of material. We're going to see that iron is a ferrous material. And what do we mean by ferrous? A ferrous material is one in which those electrons that are inside can be organized. And if we look at this diagram over here to the right, this is what we mean by organized. Over here, we see that these arrows are pointed in all these different directions, but down here, they're all pointed in the same direction. So in iron, or a ferrous material, we can take all these randomly pointed arrows and line them all up so that they all go in the same direction. What if the metal is not a ferromagnetic material? What happens? Well, like we said, the electrons are going to spin randomly with no hope of organization. So in other words, it's going to be stuck looking like this. And that means that the material is not going to be able to be magnetized. So let's think of brass, for example. Brass is a material that is not magnetic. So let's take a look at why iron can be magnetized. And iron is able to be magnetized because all the electrons are able to spin and point in the same direction. And over here we see that. Again, these little arrows are a visualization for those spinning electrons, just showing us that they're all spinning and pointing in the same direction. We need to talk about domain because we see domains here and domains there, and it says domains before, domains after, but what exactly is a domain? Well, a domain is the section inside that ferrous material. So how we have these little sections, if we were to zoom in on a piece of iron, we actually would see little sections inside that piece of iron. And within those sections, we want to make sure that all of those electrons are spinning in the same direction. Then in the next section in the same direction, and the next one, so on and so forth. The more electrons we can get to spin in the same direction, the more domains we can have that are aligned. And when we have more domains aligned, the stronger the magnetic field. Over here, I have a video in which these scientists were able to use magnets, and specifically electromagnets, to levitate non-magnetic material.
Leave it. So that was me. Actually, yes. Good.
Oh, great.
Good.
This is a nice.
Yeah, this is it.
Don't actually don't walk. Don't touch anything, please.
It says
So as you guys saw, they were able to levitate a frog, a grasshopper, and some plants. Some of you might be asking though, Mr. Weiss, how were they able to levitate stuff that wasn't made of iron? Was it the iron in the frog's blood? Was it the iron in the grasshopper? It actually wasn't. So the way how they're able to magnetize it is a simple property called magnetic induction, in which they put these objects in a very, very strong magnetic field. This magnetic field was so strong that it was able to make those electrons inside those materials, so those frogs and grasshoppers, because we know that those frogs and grasshoppers are made up of atoms, and atoms have electrons. So they were able to get all of those electrons to spin in the same direction, therefore generating a magnetic field from that object. The magnetic field of the source and the magnetic field of the frog were opposite of each other, therefore making it levitate. In order to do this, they needed a magnet that is 1,000 times stronger than your normal refrigerator magnet. In order to make a human float, they actually need a magnet, which they have, the world record magnet, but in order to do that, they need a lot of energy, because it's an electromagnet, which we'll talk about later on in the unit. But just know that we have the technology to make a human actually levitate with magnets. It's just not really plausible or makes sense at all to do, because they can only get a human to levitate about 10 centimeters off the ground. They have not tried it, but they have the technology. Now we're going to compare all the metals in the picture below in regards to those domains that we talked about. So over here, we have an unmagnetized iron, then we have a magnet itself, then we have a non-magnetic material with no domains. So the first one, we're going to say the unmagnetized iron has domains with electrons that are spinning in random directions. How do I know if they're random directions? Well, if I see here, these arrows are all pointed in different directions. Therefore, they're randomized. How do I know if there's domains? Well, we said domains are the sections within those materials. Next, I have the magnet. What do I notice? I notice all these arrows are in the same direction, so that's why it's a magnet. But we're going to say that the magnetized iron has domains, because again, there's sections here. But this time, these electrons are spinning in the same direction. That's why this guy is magnetized. Lastly, we have a non-magnetic material with no domains, and we can see that there's no domains here because there's no sections within the material. And we're just going to say that a type of material in which this is possible would be aluminum, because aluminum has no domains and can't be magnetized. All right, now we're going to take a look at a standard bar magnet and the properties of that bar magnet. First is that a bar magnet has a north and south pole. It will only have 2 poles. It will not have 3, it will not have 4, it will not have 8, it will only have 2 poles. Next, we want to say that those magnetic field lines will never cross each other, just like with the Earth. how we showed that those magnetic field lines of the Earth did not cross each other. Then we're going to say that the closer to the magnetic field, the stronger it is, which makes sense. As we get closer and closer to that magnet, we should experience a stronger and stronger magnetic field. Lastly, like poles are going to repel and unlike poles attract. So like poles such as north-north or south-south will repel, and unlike poles such as north-south or south-north will attract. Here's a picture of our bar magnet below, in which again we have this north pole and the magnetic field lines flow out of the north pole, and then the south pole in which the magnetic field lines flow into the south pole. We notice that these lines are never crossing, and we also notice that there's more magnetic field lines closer to the magnet, meaning that it is stronger by the magnet than it is away from it. Alright, now we're just going to take a look at a few situations and identify them as attracting or repelling. First one here, we have a north and south pole. These two are going to attract. The reason they're attracting is because they're opposite. Next, we have south and north. These are opposite. They're going to attract. Next, we have north and north. North and north are the same, so likes repel. And lastly, we have south-south. South and south are the same, so those are going to repel as well. Now we're just going to wrap up what we talked about. First and foremost is that magnetism is a force that can either attract or repel objects from a distance. We can abbreviate it as the B field, standing for magnetic field. Magnetic field lines are going to run out of the North Pole and into the South Pole. A ferrous material can be magnetized. And in order to do that, we need those electrons to spin in the same direction. Domains are those sections inside a ferrous material, such as iron. And when those domains are aligned, meaning that they're pointing in the same direction, the object becomes a magnet. The more alignment, the stronger the magnetic field. When there is random alignment, or they are all pointing in different directions, it will be unmagnetized. Like poles repel, and unlike poles attract, just like we said on the last slide. And lastly, magnetic field lines will never cross.